To me, take a picture and email it, or just make sure you have it turned in by the end of the day on Tuesday when you come back. Okay, that's 7.1. And now we're going to start 7.2. Ian, did I turn that on?
Yeah.
Okay. So 7.2 gets us started on our study of matrices. A matrix is a rectangular array of numbers arranged in rows and columns. That's what a matrix is. A rectangular array of numbers arranged in rows and columns. So I'm going to put an example up here. I'm going to say matrix E, and I'm making that up. It can be any letter we want. Generally, we do use capital letters. I'm going to say matrix E looks like this. Okay, there's matrix E. Notice that it has a rectangular shape, and it's full of numbers that are in rows and columns. Now, this seems so basic, but kids mess this up and it is disastrous. Rows are like in a bleachers. Rows go this way. So these are rows. This matrix has 2 rows. Columns are like at the White House. They go up and down. So these are columns. The dimensions of a matrix are its rows by columns. Now that is not a times, and it looks like a times, but it's like by. Like if you go down the Lowe's and you buy a 2x4, that's what that is. It's the dimensions of it, the size of it. So rows by columns. So what are the dimensions of matrix E? Matrix E is a 2x3. Those are its dimensions. Sometimes dimensions is referred to as order, the order of the matrix. What do you think a square, that should say matrices, let's type M-A-T-R-I-C-E-S. What are square matrices?
2x2.
So an example would be a 2x2. What do you think the definition is? Same number of rows as columns. Exactly. Just like what a square is. Length and width match. So a square matrix has the same number of rows as columns. 2x2, 3x3, 4x4, and so on. If we had a semester to study what's called linear algebra, we would go so deep into this. There's so many fascinating things. But we're not going to have all that time, so we're just skimming the surface. But square matrices do have, we can do things with squares that we can't do with other matrices. So we'll be talking about a few of those things. Dimensions, squares. Entries or elements. The entries or the elements, and both words are fine, interchangeable, are the numbers inside the matrix. So 6 is an entry. 2 is an entry. So we said it's a rectangular array of numbers. These numbers are the entries. Those are called the entries. And if I wanted to talk about, let's say, I'm talking on the phone with somebody or something, and I want to talk about this number right here. I could talk about that number by putting a lowercase e and then a subscript, so down below, 2-1. Now, first of all, the lowercase e tells me that I'm in matrix E. So if I had a whole bunch of matrices, this would tell me which one to look in. And then the 2-1, guess what that stands for? Row 2, first column, exactly. The first number, whether you're doing dimensions or identifying entries, the first number is always rows. I always think Roman Catholic, rows, columns, RC. It's always the row first and then the column, okay? Equal matrices. If I told you 2 matrices were equal, which sometimes we want to set it up that way, that matrices are equal, what do you think has to happen for two matrices to be equal? The first thing that has to happen is they have to be the same size, right? They can't be equal if one's 2 by 2 and one's 3 by 8. Those can't be equal. So they have to have the same dimensions. They don't have to be square, they just have to match. Okay? And then what else would make them equal? So same numbers, same entries. All right, so let's look at a couple here. Let's look at 1, 2, 3, 4, and 4, 3, 2, 1. Now, those two matrices have the same dimensions. They're both 2 by 2s. And they have the same numbers inside, but they're not equal. What else do we need? We need the numbers to be in the same order. That's right. So we call that same corresponding entries. Now, I know exactly what some of you are thinking. You're thinking, gosh, this is, what's the point of that? Again, we're just skimming the surface, so we're getting some fundamental definitions down, and then we'll go from there and we'll cover as much as we have time to cover. These are equal matrices, two-part definition. They have to have the same dimensions, and they have to have the same corresponding entries, which means if there's a 1 here, there has to be a 1 here, and so on. Transpose. Let me come back to my matrix E here. The transpose is denoted with a little capital T, we call that a superscript, written up above like an exponent position. The transpose of this matrix would be this. Can you tell me what a transpose is? There's an example. What is it? Rows and columns, which we say we interchange the rows and columns. So what was row 1 is now column 1. We interchange the rows and columns. And believe it or not, there are matrix operations where you need to do this. Interchange the rows and columns. So the original we said was a 2 by 3. That automatically means the transpose will be 3 by 2. Absolutely. And finally, the last definition is trace. Unfortunately, the word transpose and trace start the same way with that TRA. If you're doing the trace, if we're doing the, I can't do the trace of E, so I need a new matrix here. Let me put matrix A up here. All right, there's matrix A. If I'm doing the trace of A, and the notation for that is a little TR out in front. This is the notation for transpose. This is the notation for trace. The trace of A, this is matrix A, would be this. 13, the number 13. Did anybody see where that came from? What we call the main diagonal. So your definition for trace is, if A is n by n, okay, let's stop right there. If the matrix is n by n, what does that mean about it? It's square. 3 by 3, 5 by 5. So I don't know if you were listening or not, but I was going to do the trace of E, and then I looked over here and said, oops, I can't. Because the only way you can have a trace is if your matrix is square. So there's no trace for E. But I can do a trace here, and it's the entry that's in the 1, 1 spot, first row, first column, plus, what's the next one? What entry is this right here? That's the 2, 2 spot, plus, And if the matrix is bigger, it's going to go all the way to the NN number. So if it, 4, 4, 5, 5, 6, 6, however big it is, that's the trace. What, Meg? A11. That's A sub 1, 1. Entry, that's the entry that's in the first row, first column. We talked about earlier, a little E. Only it's a little a because this is matrix A. So it's the 1, 1 spot, the 2, 2 spot, the 3, 3 spot, and so on.
It's just referencing that diagonal.
Yes.
Okay.
This is how we denote the main diagonal. Yeah, that's the definition right there. This is the definition. Okay, so now we're ready to actually do some stuff. Yes, the transpose is the new matrix form when you interchange the rows and columns. You may have never worked with a matrix before in your life, but you can do this problem. I am 100% sure that you can do this problem. Take a wild guess. What do you think we do? We're going to add these two matrices together. This is problem 2A. What do you think? Yep, so that's going to be a 7. This is going to be a 1, 3, and 1. How does that look to everybody? Beautiful. How about the next one? A plus 2B. What do you think 2B? What do I do with 2B? Huh? It's like distributive property. We just take 2 times everything in B. So that's going to be 12, 6, 0, and negative 8. By the way, this 2 has a special name. It's called a scalar. Who's in physics? Have you heard that word before in physics? Yep, what's a scalar? Basically, it's just a number, right? Just a number. When we say something is moving at 12 miles an hour, 12 is a scalar. Okay. So the answer is, we're ready for the answer now. The answer is 13, 4, 3, and negative 3. How does that look? Is that okay with everybody? So easy. 2A plus B. Does this bother you? What bothers you?
Well, they're not the same.
They're not the same size, so I'm not going to be able to match these entries up to add them, right? Can't do it. That's an impossible problem. If you want to add or subtract matrices, they must be the same size. In other words, they must have the same dimensions. They do not need to be square, but they need to match if you're going to add them. That makes sense? Okay. All right, now hold on to your hats, because now we're going to multiply. Okay? And the rules for multiplication are different, and it's a little bit more of a process, but you will get it. It's easy. So AB is A times B. All right. Here's the rule. Before you start trying to multiply, figure out the dimensions of each of your matrices. Now this is an easy one, so stay with me. What are the dimensions of this matrix? 2 by 2. What are the dimensions of this matrix? 2 by 2. When you multiply, they don't have to match exactly. The only part that has to match is right here. In other words, the columns of the first have to match the rows of the second. Now with addition, they have to match exactly. But with multiplication, only these have to match. So I could have a 5 by 8 and an 8 by 3, and I can multiply those. Furthermore, the product, the answer, will have these dimensions. So the middle two have to match, and the outside two tell you how big your answer is. So in this example, how big would my product be? 5 by 3. All right, that's the rule for multiplication. Everybody got it? All right, so now I know I am going to build a new matrix that you don't have to draw these boxes, I am, because we've never done this before. We have to fill in these boxes. Our answer is going to have 2 rows and 2 columns. So now I have to figure out what all these numbers are. Here's how I do it. To find this number right here, that number is in row 1, column 1. So I take the numbers in row 1, 1 and -2, and I multiply them times the numbers in column 1, 6 and 0. So look at my color coding. This is the process. These are called inner products. This is how we do it. So I take 1 times 6, -2 times 0, and I add them together, and that is the number that goes in that spot. So that's going to be a 6. Then, this number, I will multiply my first row times my second column and add them together. So what's that going to be? 7. All right, now I'm going to do this spot. Well, what spot is this? This is the second row, first column. So I'm going to take my second row times my first column. So my second row times my first column, multiply and add. So what am I coming up with there? Looks like I get 18. And then finally, I'll take brown times blue. First row, second column. Add them together, and what do I get? -11? Coincidence? There's no, I mean, there's nothing going on there, that just happened. Okay, multiplication is a pain in the butt, but that's how we do it. So now we've got D times C. Before I write all this out, D times C, let's see if we can do it. What are the dimensions of D? 2 by 3. What are the dimensions of C? Oh boy, I can do it, right? So I am going to multiply D times C. Come on guys, we're going to do 2 problems and then we're going to be done for the day. You're gonna be done with math for a week, unfortunately. All right, how big's our answer gonna be?
2 by 3.
Our answer is going to be another 2 by 3, so it's gonna have 2 rows and 3 columns. Okay, so I'm gonna fill in all those blanks. Okay, I'm not gonna color code this time, I think you got the idea. What am I gonna multiply to find this number right here? Always row first, so row 1, column 1.
2 and
So
1.
this guy times this guy. So 2, -1, 3, write your row. And then next to it, write your column. 1, 0, 1. See how I'm pairing them up? Multiply and add, and it looks like that first number is a, that's 0. I think it's 5, isn't it? Remember, when you times by 0, you get 0, so 2 plus 3, that's a 5. Now, what's gonna happen here? Still row 1, so I'm still using 2, -1, 3, but now I'm using column 2. -1, 3, 4. It's a 7. Yeah, get those post-lunch brains working there, guys. And then 2, -1, 3 again, but this time times 2, -1, 0. It's 5. 4 plus 1 is 5. All right, now, okay, so now I'm ready for the bottom row, so I'm gonna do exactly what I just did, except I'll be using 5, 1, 4. So I'm gonna use 5, 1, 4 with my first column. 5, 1, 4 with my second column. And 5, 1, 4 with my third column. I think I got 9. Check my arithmetic, it's really easy to make mistakes
Yeah,
here.
it's 9.
14
Yep.
and 9 again. Again, total coincidence I have matching numbers in there. Please don't think there's any kind of pattern. Anybody have any question about any of those numbers? Everybody getting those numbers? You're like, unless we're just shut up. Nope, one more problem.
Oh.
One more problem. A times C, this is letter F. Can't do it. Why can't we do A times C?
Because the column and the row doesn't match.
Yeah, it's a 2 by 2 times a 3 by 3, and these two numbers aren't the same. So no answer, cannot do letter F. You guys are too